The film Interstellar presents a future filled with great challenges. Our Earth is dying, crops are failing, and vast dust storms are a common sight. Humanity faces a desperate search for a new home amongst the stars. This urgent search leads brave astronauts on an incredible journey far from our solar system. They must travel through a mysterious wormhole to explore a distant galaxy. Their mission is absolutely vital for the survival of everyone left behind on Earth. Along their perilous path, they encounter many strange and wondrous cosmic phenomena. One of the most mind-bending of these concepts is how time itself can behave differently. It does not always flow at the same steady, predictable pace we experience in our daily lives. This idea is central to their dangerous and emotional adventure. We often think of time as constant. A second is always a second. A minute is always a minute, no matter where you are or what you are doing. This is true for most of our experiences on Earth. However, the laws of physics, particularly Albert Einstein's theories of relativity, paint a different picture. Einstein showed that time is not absolute. Instead, time is relative. It can stretch and it can shrink. Its passage can change depending on certain conditions. Two main factors cause this: how fast you are moving and how strong the gravity is around you. This might seem like science fiction, but it is a proven part of how our universe works. In the story of Interstellar, the crew of the specialized spacecraft Endurance travel immense distances. Their journey takes them very close to incredibly massive objects, such as the supermassive black hole they name Gargantua. These colossal objects possess extraordinarily strong gravitational fields. This intense gravity has a profound and measurable effect on the flow of time. For the astronauts venturing near such a powerful gravitational source, time passes much more slowly compared to how it passes for people far away, like those back on Earth, or even for crew members remaining on their ship at a safer distance. This slowing of time becomes a critical element, posing significant challenges and heart-wrenching consequences for their mission. This fascinating idea, known scientifically as time dilation, is not merely a clever plot device for films. It is a very real physical phenomenon. Scientists have conducted experiments that confirm its existence. For example, highly accurate atomic clocks flown on fast aeroplanes show tiny differences in elapsed time compared to identical clocks on the ground. Furthermore, the Global Positioning System, or GPS, satellites that many of us rely on every day for navigation, must continuously account for both speed-related and gravity-related time dilation. If they did not, the system's accuracy would quickly drift, leading to significant errors. So, Interstellar uses established scientific principles to explore the dramatic human impact of these extreme cosmic conditions. What precisely causes time to slow down so dramatically near a black hole? The answer lies in the fundamental nature of gravity. The brilliant physicist Albert Einstein provided us with the deepest understanding of gravity through his theory of general relativity. He revolutionized our thinking by proposing that massive objects do not just pull on other objects with a mysterious force. Instead, he explained that massive objects actually warp or bend the very fabric of the universe, something he called space-time. Space-time is not just the three dimensions of space we are familiar with. It intricately combines space with the fourth dimension, time, into a single unified continuum. This concept is key to understanding time's strange behavior. Imagine space-time as a vast, flexible rubber sheet stretched out taut. If you place a light object, like a marble, onto this sheet, it will create a small dimple. If you then place a much heavier object, like a bowling ball, onto the sheet, it will create a much deeper and wider curve. This analogy helps to visualize how celestial bodies affect space-time. A planet creates a certain amount of curvature, a star creates more. A black hole, being an object of immense mass concentrated into an incredibly small space, creates an extraordinarily deep and steep curve in space-time. This extreme curvature profoundly influences everything that comes near it, including the passage of light and, crucially, the flow of time itself. Near a black hole, the gravitational pull is unimaginably strong. This is because so much mass is packed into such a tiny volume. As a result, space-time in its vicinity is extremely curved. For an astronaut or any observer positioned close to the black hole, time would pass significantly more slowly compared to an observer situated much further away in a region of weaker gravity. It is as if time itself is being stretched and distorted by the immense gravitational forces at play. This effect is not a minor adjustment. The difference in the rate of time passing can be enormous, leading to hours for one person equaling many years for another, as depicted in Interstellar. Therefore, the closer an object or a person gets to a powerful source of gravity, the slower their personal clock will tick relative to an observer who is located in a weaker gravitational field. This phenomenon is specifically known as gravitational time dilation. It is a direct and fundamental consequence of Einstein's groundbreaking theory of general relativity, which has been repeatedly verified through observation and experiment. The film Interstellar brilliantly harnesses this very real scientific principle to create some of its most dramatic and emotionally charged situations, forcing its characters to confront the tangible costs of interacting with such extreme cosmic environments. In the captivating film Interstellar, the brave crew of the Endurance directly confronts the harsh realities of gravitational time dilation. Their mission necessitates a visit to a potentially habitable world designated as Miller's Planet. This planet has a critical characteristic. It orbits incredibly close to the supermassive black hole, Gargantua. This proximity to Gargantua's immense gravitational field has a drastic and inescapable impact on the flow of time on the planet's surface. The astronauts, Cooper, Amelia, and Doyle, are fully aware of this perilous time differential before they even begin their descent in the landing craft. They know every moment spent there will cost them dearly in terms of time lost elsewhere. The calculations are stark and unforgiving. On Miller's Planet, every single hour that passes for the landing party is equivalent to 7 long years passing for anyone located far from Gargantua's gravitational influence. This includes the general populace back on Earth, but more immediately, it applies to their fellow astronaut, Romilly. He remains aboard the Endurance mothership, maintaining a wider, safer orbit around the black hole, where time flows much more normally relative to Earth. This sets up an astonishingly severe time difference between the surface team and Romilly. The astronauts on Miller's Planet are under immense pressure to conduct their survey and retrieve data as swiftly as humanly possible, knowing the clock is ticking at an accelerated rate for the rest of the universe. Upon landing, the team's carefully laid plans quickly encounter severe problems. The planet is covered by a shallow ocean, and they are soon confronted by colossal tidal waves generated by Gargantua's gravity. These waves cause significant delays and lead to the tragic loss of Doyle. In total, Cooper and Amelia spend only a few precious hours on the hazardous surface of Miller's Planet. However, when they finally manage to escape the planet's gravitational grip and return to the Endurance, they are met with a shocking reality. Over 23 years have passed for Romilly. He has aged significantly, spending 2 decades in solitude, while they have aged merely a few hours. This scene powerfully illustrates the disorientating effects of extreme time dilation. This experience is profoundly affecting and serves as a stark demonstration of the immense personal and emotional cost of exploring such extreme cosmic environments. The astronauts did not just lose valuable mission time, they lost irreplaceable years of their lives relative to those they left behind. For Cooper, this meant his children on Earth were growing up, aging decades while he experienced only hours. This segment of Interstellar powerfully translates the abstract scientific concept of time dilation into a tangible, heart-wrenching human drama. It underscores how the fundamental laws of physics can have deeply personal and irreversible consequences for intrepid explorers venturing into the unknown depths of space. Later in the narrative of Interstellar, the protagonist, Cooper, finds himself in an even more extraordinary situation. After detaching his section of the ship to propel Amelia Brand towards the remaining potentially habitable planet, he falls into the black hole, Gargantua. Miraculously, he does not encounter a destructive singularity as standard theories might predict for an unprotected entry. Instead, he is depicted as entering a complex, multi-dimensional structure known as the Tesseract. This tesseract is portrayed as a construct created by advanced future humans. It allows Cooper to perceive his daughter Murph's childhood bedroom across various points in her past, effectively enabling him to navigate through time, though not physically enter it. This is a more speculative, though thematically rich, element of the film. From within this strange, higher-dimensional space of the tesseract, Cooper faces the urgent challenge of communicating vital information back to his daughter, Murph, in her past. He needs to transmit the quantum data that he and the robot TARS have collected from within the black hole. This data is crucial for solving the gravitational equation that will allow humanity to escape the dying Earth. He cannot directly interact with objects or people in the past in a conventional sense. However, he discovers that he can exert influence through the fundamental force of gravity. He learns to manipulate gravitational waves, which, in the film's logic, can propagate through space-time and potentially across time to affect objects in Murph's room. Using this newfound ability, Cooper painstakingly sends the complex quantum data to Murph. He does this by creating gravitational anomalies that translate into Morse code. He subtly pushes books from her shelf in specific sequences. More significantly, he manipulates the second hand of a wristwatch he had given her before he left Earth. The adult Murph, now a brilliant physicist herself, eventually recognizes these anomalies as intelligent signals from her father. This allows her to decode the data, complete the gravitational equation, and ultimately devise the technology for humanity's mass exodus. Thus, in Interstellar, gravity is not only a force that warps time, but also a medium for extraordinary communication across dimensions and epochs. Understanding these profound concepts about space, time, and gravity is not just an academic exercise. It is deeply important. It helps us to comprehend the vast and intricate universe in which we live. Such explorations push the boundaries of scientific knowledge and can inspire new technological advancements. Films like Interstellar, while taking some creative liberties, play a valuable role in popularizing these complex scientific ideas. They can ignite curiosity and encourage people, especially younger generations, to learn more about physics and cosmology. Knowing about phenomena like time dilation and the properties of black holes expands our perspective on reality and our place within the cosmos. This knowledge is fundamental for future space exploration and for deepening our understanding of the universe itself.